So, last class we have been talking about circuits, right, Boolean circuits. So, we showed interesting results like if NP is contained in P slash poly or X is contained in P slash poly, then what happens? Basically, polynomial hierarchy collapses and some very surprising or uh, weird things happen which we don't believe. And then we started another reason. We started explaining this main reason of defining Boolean circuits, which is to model parallel computation in contrast to the sequential way of solving problems, which is Turing machine. Turing machine is step by step. It's just one processor which is doing the computation. Instead, in parallel algorithms, we want many processors, right? So, many Turing machines. How do we model that? So, for that we say that if you have poly n processors, think of them as these AND or NOT gates, and the connections between them are the wires, and the depth of the circuit we want to be log n, poly log n, which is the time complexity. Okay, so this we will call efficient parallel algorithm, which has poly n many gates or processors, and the depth is poly log n, which corresponds to poly log n time in parallel, right. So, this should be true for all x's of all lengths. So, again for different n, the circuit may look very different, the algorithm, parallel algorithm may look different, because after all you have to take these many processors, poly n many processors, that is growing with n, right. So, this is a concept where circuit is a natural construction or concept. Then application of this you can see in parallel algorithms, like adding two n-bit numbers in parallel. So, if you do it sequentially, it will take order n time, but if you use many processors, order n processors, then you can actually do it in order log n time. Okay, that I leave as an exercise. So, now this is nicely captured by Boolean circuits. Of depth poly log n. Okay, so poly n size and poly log n depth. This is like time, and size is like the processors, number of processors. And with that, we can now formally define what is called Nix class. Okay, Nix is the nickname of Nicholas Pippinger, who is credited with studying this for the first time. So, any language L is said to be in NCD. NCD is the new complexity class, D some constant, if there exists a circuit C in fact, I should say if there exists a constant C greater than 0 and there exists an L uniform log space uniform circuit family Cn with size as I said, we want size to be only polynomial in n. So, size is less than equal to n to the c, and c is an absolute constant, and Cn is a circuit. As n grows, it becomes a circuit family, which can be computed in, the connections can be computed in log space. Okay, that is what the uniformity means. So, it is a log space uniform circuit family. You can actually produce the circuits very efficiently. Surely in polynomial time you can produce them. And depth, most importantly, is at most log n to the d. Okay, so this d is the parameter of the complexity class. So, for constant d, say d equal to 0, what does d equal to 0 mean? It means that, yeah, okay, so let me put a big O here. So, d equal to 0 means that depth is constant, right, that is NC 0. NC 1 means depth is log n, and size always is only polynomial size is allowed. Okay, so these are classes NCDs such that the circuit family Cn computes L. So, for all x 0 1 to the n, x is contained in L, x is a yes string if and only if Cn x is 1. Okay, so Cn solves L using poly n gates log n d. So, polylog depth, and based on this you immediately get the complexity class NC, that is Nix class, which is union over all NCDs. Okay, so in this remember, I should have mentioned this, that the fan-in is constant. So, here the fan-in of Cn is assumed to be constant. Okay, so this is the constant fan-in version of circuit which we are talking about. So, in constant fan-in, the depth is log n to the d. We can also make the fan-in. So, fan-in is how many inputs are entering a gate, right? That we are fixing to be 2. We can also allow fan-in. We could also allow arbitrary fan-in. And in that case, it has a different name. Then it is called ACD. So, L is in ACD, kind of another class, short form for another class. If Cn, if the circuits Cn above have fan-in unbounded. Unbounded means that it is allowed up to the size. Okay, so fan-in cannot exceed the size of the overall size of the circuit, but it can be as big as that. So, anything is allowed. When anything is allowed, we call it unbounded fan-in, and we call the problems that you are solving ACD. That is the complexity class. Okay, and we can also take that union and call it AC. Now, an easy observation is that NCD is contained in ACD, because NCD has fan-in 2 while constant, while ACD has any unbounded fanning, so it's clearly contained. And moreover, ACD you can do in NCD D+1. Why is that? So the idea is if a gate has S inputs, then we can simulate it in log S depth fan-in 2 circuit. Right, you can check this as follows. So suppose you had 4 inputs. Okay, so you had 1, 2, 3, 4 inputs, and you were computing a gate on these 4. So instead you can do it 2 at a time. So first you compute these 2, and then these 2, and next you compute these 2. Right, so you can break it up, this output that is being computed. Instead of computing it at once, you can compute it in 2 steps. So that is depth 2 and also fan-in 2. So via this reduction, inputs, if they are if the fan-in is poly n, then you can blow up the depth and reduce the fan-in. So this means that fan-in poly n or fan-in n to the C size or depth log dn translates to you can manage in fan-in 2 and increase the depth. Okay, so that is the claim, that ACD can be computed in NCD plus 1. That finishes the proof. And by this containment, so we have sandwiched ACD in NCs, and hence AC and NC are equal. They are equal, and in terms of time, what does it mean? Well, since this is parallel algorithm, it's also sequential, so it's in P. Okay, that should be clear. And the open question, of course, here is whether NC is a subset of proper subset of P or not, right? Which is like asking, can every algorithm be made parallel? Okay, an efficient algorithm, can it always be made parallel? And we don't expect so. So we conjecture is that NC is not equal to P, but this is an open question. So as an exercise, I leave it to you that this NC0 is smaller than, strictly smaller than AC0, and AC0 is strictly smaller than NC1. Okay, I leave this to you. It has a simple proof. So NC0 is, since the depth is constant and the fan-in is also constant, these are actually local functions, constant locality. It cannot solve anything more than that. Any function that you compute in NC0, every bit, I mean the output bit will depend on only constant many inputs, right? Because the fan-in is constant, depth is constant. While this is more complicated, so here you use parity. Okay, so parity function you can compute in NC1 again by this doubling procedure, recursive procedure. You do it 2 at a time. So you can compute parity in log n depth, constant fan-in 2, but you cannot compute in AC0. Okay, so this is a very interesting result and not easy. Okay, you can try your hands at this. We do such things in advanced courses. And yeah, so the meta theorem here is any language L has efficient parallel algorithms if and only if it is in NC. Okay, take this more as a definition of efficient parallel algorithms. Okay, if you can find an NC circuit, then it is solvable in parallel polynomial time. Okay, we can also compare this class NC1 AC1 with log space. So depth of the circuit okay, depth corresponds to parallel time, but it also corresponds to sequential space. Okay, so if you actually simulate this circuit by a Turing machine, then the space required really depends on the depth of the circuit, right? This is natural because the depth, I mean, unless you compute the previous the value below, you cannot go up, right? So that much of memory you need to have. That is the rough idea. Formally, what we will show is this theorem that NC1 is contained in is simulable in log space, which you know is in NL, which actually is simulable in AC1. So why is NC1 in L? How do you show this? Basically, in a circuit, what you can 2 is and here you have a variable, okay, and here you have the circuit value, and rest you have some circuit connections. So this path that we have drawn from xi to c, this has depth log n. And so the way you can simulate the computation of this circuit just in log n space, is by recursion. Okay, so basically compute start from the root and compute its inputs by recursion. Reusing the space. So the recurrence for this procedure, right, if you start at the root, it has 2 inputs, compute those recursively, reusing the space. So the recurrence for space becomes is S of L less than equal to S of L minus 1 plus. So when you go down, then you are going deeper into the circuit, right? So L is in the top, it is log n, and then when you go below, it is L minus 1. So here it is level L, while when you go below, it is L minus 1, and it can only reduce log n, order log n many times, right? So once you have the 2 inputs, then the space needed is only constant. So that's order 1. Okay, so this is the space requirement. It is SL is equal to SL minus 1 plus order 1, which gives you SL is order L. So you just need log space for this simulation. Yeah, CX computation. CX is computable in log space. So NC1 is in L. That's what we have shown. L is clearly in NL, that is trivial, and why is NL in AC1? Let's focus on that. So for this, you basically express, so let L be a problem in NL with Turing machine M and input X of length n. Right, this is the setting. You have a problem in NL, L with Turing machine M, which only takes log space, but it's a NDTM. And it is running on input X. So, what is the number of configurations? So, number of configurations is 2 raised to the space, right, which is at most 2 raised to log n. Let us call that bound big N. So, there are big N many configurations, it is basically poly in N, and how the NDTM moves from one configuration to the next, there are many options, right, it is an NDTM. So, we can express this as a configuration graph. Let us call the adjacency matrix A. Let A be the adjacency matrix of the configuration graph. Of Mx, M on input X, right. Let A be the adjacency matrix, and now all you have to do is to check whether the start configuration is connected to the accept configuration. That is all you want to check, right. So, this reduces to computing E to the N matrix powering. Or in fact Boolean matrix powering. E to the N, right. That is what you basically want to check, that in n steps whether you can reach from C start to C accept within n steps. So, you have to compute this e to the n power. So, by repeated squaring compute this in AC1. Okay, this you can do easily. So, again NL in AC1, what you do is you express this as a, as a matrix powering question. What is the matrix? The matrix is basically the adjacency matrix of the configuration graph of the NDTM on a certain input. This NDTM only requires log space, so the configuration graph is not too big. Adjacency matrix is big N times big N. So, you have to compute this e to the n and check an entry and checking an entry or testing an entry. This entry which you will check is this is C start row, C accept column, whether that entry is 1, right. So, you just have to compute one entry of this powering. So, the way you do it is by repeated squaring. So, you compute a square, a to the 4, a to the 8 dot dot a to the n, this is only log n steps, and so you can express this as a circuit of log n depth with unbounded fan in. So that's exactly AC1. Okay, so you can simulate NL in AC1 and NC1 in log space. Okay, that's the gap between NC1 and AC1. And remember that all these things they are living in NC2. Right, so we have a classification or complexity classes, famous complexity classes between NC1 and NC2. So that is a nice result to know, and using this log space, now we will do something new, which is P completeness. So is there a P complete problem? So we call problem B P hard if for all problems in P, for any problem A in P, A can be reduced to B. Now, if we say polynomial time reducible, that will not give you anything interesting. We'll make it stronger. We'll say that within log space you should be able to reduce. So if A, we had this implicit reduction concept, right? So the same thing, implicitly L reduces to B. Okay, so A should L reduce to B implicitly, meaning that bit by bit there is a log space reduction. Of course, in log space you cannot produce all the bits, that will need more than log n space, but a single bit, I mean X string of A can be mapped to some string Y, and bit by bit it's a log space reduction. Okay, then we call B P hard, and of course P completeness will be additionally if B is in P, then we call B P complete. Okay, so that is the notion of P completeness. It's kind of the hardest problem in the deterministic polynomial time class. So are there such problems? So does there exist a natural, focus is on natural, P complete problem? Okay, so this is what we will define next.